Assalamualaikum warahmatullahi wabarakatuh. Today I will explain about Boolean algebra and digital logic. Boolean algebra is a mathematical system for the manipulation of variables that can have either one of two values. So in formal logic, this value can be true and false. In digital systems or in system computers, this value are on and off, 1 and 0 or high and low. So specifically, if the binary value is 1, so in binary Boolean algebra, it can be true, and then 0 will be false. Common Boolean operators include and or and not. So basically, the Boolean algebra consists of these three operators. Okay, as for the not operators, okay, the complement represents the inverse of a variable and is indicated with an over bar. Thus, the complement of A is A bar or A prime. Okay, Boolean operator can be completely described using a truth table. So, inside the truth table, we can generate the Boolean function or Boolean algebra. Okay, Boolean algebra, and then truth table also can generate logic circuit. Okay, logic circuit. Right. So how to build a truth table, it depends on the number of the input. For example, let's say you have one input. Okay, so one input means 2 power of n is equal the number of the combination. Okay, number of combination on the truth table. Okay, so from that combination, then we can run the, or we can calculate the result of that Boolean function. So it depends on the number of input. Here, we only have one input for the NOT logic. So 2 power of 1 is equal to 2. So in this case, the combination of the truth table will be either 0 and 1. Okay, so let's say if it's an AND operator. AND operator consists of two input. Okay, at least two input. So X and Y. So because we have two input, you would have 4 combination. Okay, so 4 combination, it start from all 0 until all 1. So how to build up this combination? It start from 0 and then we add 1. Okay, you will add 1 and then add 1 again, you will get 1, 0, and then add 1 again, 1, 0, add 1, you will get 1, 1. So if you convert it into decimal, you will get this is 0, this is 1, this is 2, this is 3. So 0, 1, 2, 3 means 4 combination. So what about 3 input? So 2 power of 3 is 8, and then 4 input is 2 power of 4 is 16. So this combination start from 0 and then you add 1, add 1, add 1. Okay, and then that is for the left side or left column, whereby this is your input and then this is your output. Your output depends on the function itself. Okay, what type of functions that we specify in that truth table. Okay, but for a basic Boolean algebra, okay, we learn a bit. We know that AND is consists of a Boolean product, or we can say like a multiply. Okay, except that the result or the output is in one digit. Okay, so 0 and 0, or 0 multiplied by 0 is 0. Then 0 multiplied by 1 is 0. Okay, 1 multiplied by 0 is 0. And then 1 and 1 is 1. So it means, okay, it says here that if all the input is 1, then your output will become 1. Okay, on contrary to the OR operator, it is a Boolean sum, like an addition. But as I said before, it only consists of one digit. Okay, one digit. So one bit. So it doesn't add, but the action is like an summation or addition. Okay, so for example, or 0, 0 or 0. Okay, 0 or 0 is 0. 0 or 1 is 1, and then 1 or 0 is 1, and then 1 or 1 is 1. So in conclusion, OR operator would produce 1 if at least one input has one big 1. Okay. Whereas for the NOT operation is most often designated by an overbar here. The function is like it invert the value of the input. So let's say the input is 0, then the output will become 1, whereas input 1 would be invert to 0. Okay, so that's why I'm saying that x bar or x naught is also can be said that it is a complement. Okay, right. Now, once we have the truth table for the Boolean function, okay, so we need a function. Okay, for the Boolean function, we need a function. So from this function, okay, we calculate or we identify the number of input. We have x, z plus y. Okay, x, z bar plus y means that we have input x, z, and y. So since we have 3 inputs, you would have 2 power of 3 equal to 8 combination. So 0, 0, 0, plus 1, plus 1, plus 1 until all 1. So you will get 8 combination. Now, to get the complete truth table, we need the output. But sometimes the function can be complicated. So the easiest way is to dissect each of these operator. Okay, for example, okay, we dissect the first priority, which is the NOT. Okay, the NOT one is the highest priority, so we build up the column Z bar. Okay, and then if say Z bar means that we look into the column of Z. If it's a 0, it will become 1. If it's a 1, it becomes 0. And then the next highest priority, the next priority will be AND. X and Z bar. So add a column of X, Z bar. Okay, so we AND it together. Okay, the previous column, which is a Z bar, we AND it together with the X. So here 1 and 0 is 0. And then 0 and 0 is 0. And then 1 and 0 is 0. And then 0 and 0 is 0. Okay, the next one will be 1 and 1 is 1. Okay, and then 0 and 1 is 0. 1 and 1 is 1. And then 1 and 1, 0 and 1 is 0. Okay, and then we OR it, okay, with y, which is the final, is a complete function. So what we had is the final function, which is f is equal to xz bar plus y. So we take out the xz bar and then we OR it with y. Okay, 0 or 0 is 0, 0 or 0 is 0. Now 1 plus 0 is 1. Now 1 plus 0 is 1. And then 0 plus 1 is 1. 0 plus 0 is 0. Like that. Okay, so this is the, once we have the result of the output, what's next? We must build up the forms, SOP and PL or POS form. So Boolean expressions can be written in the sum of products, or the simplified forms is SOP, or in the product of sum form, POS. Okay, so an expression is an SOP form when two or more product terms are summed as in the following example. A and B is A product B is summed together with A product B product C. Okay, although it doesn't have any dot there. Okay, we know that this is a product. ABC is a product itself. AB is a product. We sum it together. It's also the same for this expression, SOP expression. So how to build up the SOP expression? It's formed based on the output, okay, on the output column with the value of 1. Okay, as for the for the POS, okay, it's formed from the two or more sum terms. In this case, the example is that A sum B and then A sum C is product together. Okay, so how do we form the POS expression? Based on the output of 0. Okay, example. From the previous truth table, we can see that we have 0, 0, 0. So 3, 0, and then 5, bit 1. So for SOP, it's quite easy. Okay, look at the bit 1 here. So you can build up from this expression. Okay, 0, 1, 0. Okay, so we translate it to the uh, input name, which is for 0 for column X, we put a bar. And then for bit 1 for Y, we just add it as usual. And then for 0 for Z, we put a bar at the top. Okay. And then for this one is X bar, okay, Y, Z. And then X, Y bar, Z bar for this one. Okay, and then for this one is X, Y, Z bar and X, Y, Z. So if all of bit 1 has been termed together as an SOP, so we can combine it. We sum it together. We sum it. So X bar, Y, Z bar, sum X, Y, X bar, sorry, X bar, Y, Z plus X, Y bar, Z bar plus X, Y, Z bar plus X, Y, Z. Okay, so that is for SOP. Okay, this is for SOP. So how to build up POS? So let me change my pen and look at the output 0. So POS is formed from the sum, okay, sum of the input. So here 0, 0, 0, we previously on SOP, 0 is a bar, right? But for POS, 0 is considered as neutral. So X plus Y plus Z. Okay, and then for the second one, okay, 0, 0, 1 means X plus Y. Now, this is interesting. 1 here for Z is a convert, a bar. Okay, it's a bar for POS. Okay, lastly, this one is 101. So means that X bar plus Y plus Z bar. Okay, so to write the POS, you can write it as F X plus Y plus Z. We factor it or we product it with X plus Y plus Z bar and product it again with another term X bar plus Y plus Z bar. Okay, so this is how we build up the truth table. Okay, let's continue. Okay, once we have built up the truth table, okay, we either can simplify it, okay, using the laws of Boolean algebra, which it's to consists of rules to simplify the Boolean algebra, or using the K-map, okay, Carnot map. So first, for laws of Boolean algebra, so there are rules that we can use to simplify the algebra, such as the commutative laws. The commutative laws are applied to addition and multiplication. For addition, the commutative law states, in terms of the result, the order in which variables are odd makes no difference. For example, if the expression is a plus b, it can be represented with b plus a. For multiplication, the commutative law states that in terms of the result, the order in which variables are ended also makes no difference. So you can say AB is equal to BA, B and A. And then for associative laws, for addition, the associative law states when ordering more than two variables, the result is the same regardless of the grouping of the variables. Okay, let's say if you want to simplify it by using a grouping. So grouping can be either A plus group B plus C is also equal to grouping of A plus B and then close it and then with plus C. Okay, so for multiplication, the associative law states when adding more than two variables, the result is the same regardless of the grouping of the variables. Where if you factorize, okay, B, C, and then put an A outside, it's also the same as you factorize AB and then put a C outside. Okay, so even if you change the method of changing it, it must be on the same mode. Okay, means A and B and C, and then we can do the we can apply the associative laws. Okay. All right, for distributive law is the factoring law. Common variable can be factored from an expression just as in ordinary algebra. That is, AB plus AC is equal to, we factorize A outside as the factor inside the grouping, which is a B plus C. So in this case, if you reverse it, we can factor back again or multiply back again. AB plus AC means that you will get the same result. Okay, how to prove this? You can either use other Boolean rules, or okay, the most direct one is to use the truth table. Okay, build up two truth table. One side, left side is AB plus AC, and then the right side is A factor by B plus C. Okay, so the distributive law can be illustrated with the equivalent circuits. A factorized with B plus C, okay, which is equivalent to AB plus AC. Okay, note that, okay, they are using the same, on the left side, they are using the same input, and then they will produce the same output. Okay, so for each of the gate, produce or write down the expression so that you will get the output, the final output. Okay, and for the right side here, okay, although they are the same input, okay, sometimes the representation can be they use a multiple input that have the same input value. Okay, so in this case, as you can see, AB and AC here, actually A here comes from the same input. Right, what are other rules of Boolean algebra that we can apply? Okay, A plus 0 is A regardless the value of A. Okay, if we plus it with 0, you will get A. So let's say A is 0, then 0 plus 0 is 0. If A is 1, then 1 plus 0 is 1. Okay, and then A plus 1 is equal to 1. Okay, means that regardless of the A, if we add it with 1, so means that the value will become 1. Okay, and then A multiplied by 0 means that regardless of the value of A, if we multiply by 0, you will get output 0. And then A plus A dot 1 means that it depends on the value of A. Okay, so if A is 0, then you will get value of A, which is 0. But if the A is 1, then you will get the value of 1. And then A plus A, okay, means it's a duplicate, can be cancelled out. One of the duplicate, one of the copy can be cancelled out. Okay, and also the reverse can apply, whereby you can say A is equal to A plus A. Right? So and then A plus A bar is equal to 1. Okay, do note that A bar means that is the reverse value of A. So let's say A is 0, then A bar is 1. So 0 plus 1 is 1. Now A dot A is equal to A. Okay, means that a copy product of A can be cancelled out or can be reduced to become an A. Well, A dot A bar, A product A bar means that either of this input will become a 0, then it's totally, we can cancel it out to become a 0. Okay, now a bar, a double bar. Okay, if it's a bar, it will reverse the value. But then if you put another bar, then it will cancel out the inverse. Okay, it will cancel out the inverse, then it will become a neutral. So in this case, a double bar is equal to E. Then A plus AB, okay, is equal to A. So here, we can factor it A plus AB as A1 plus B. So imagine if you can factor it like this. So 1 plus B, 1, A plus 1. We use the rules of A plus 1, so we can say A1. So A dot 1 is equal to A, so you can say A. So that's why A plus AB is equal to A. Now, A plus A prime B is equal to A plus B. So this I would explain later during the lab. But if you come around with A plus an inverse of A dot B, so you will get A plus B. Also, we can say B plus AB prime. You can also say that B plus A. Right? So A plus B and then factor with or multiply by A plus C is equivalent to A plus BC. Okay, so this also can be explained later on during the lab session. Right. Another Boolean identities or Boolean rules, okay, is the De Morgan theorems. Okay, the De Morgan theorems explain that the complement of two or more ended variables is equivalent to the OR of the complements of the individual variables. So let's say if we have a full bar, okay, bar is on the full term. On this term is AB, so they have a bar here. So to simplify it, it's much more easier if we have a separate bar or separate invert. So to separate it, it also can be said, okay, A product B or A and B, okay, to separate the full bar, okay. So it's equivalent to A bar plus B bar. So here, N become a plus, and then you can separate between these two. Okay, these two operator. Okay, and then for the complement of two or more odd variables. Okay, so A plus B full bar. Okay, so we can separate it by changing the value, changing the operation. So plus become ended. Okay, plus become an ended. Now plus become an ended. Now we can put a single bar on each of the variables. Okay, note that it can be reversed. So A prime dot B prime is equivalent to A plus B prime. Okay, so that's De Morgan theorems. As I said before, between these two variables or these two functions, we can prove it by using the truth table. Okay, create a truth table for A plus B full bar and then A prime dot B prime. Okay, so look at the output. You will see you should get the same output. Okay, for example, logic simplification using a Boolean algebra can be reduced, okay, or changed to a more convenient form. Okay, let's say this is a functions, okay, coming from the truth table. So you will get AB plus A factor by B plus C plus B factor by B plus C. So we use a distributive law where we factorize it. AB plus AB. Okay, we remove the grouping. So AB plus AC and then remove the grouping for B plus C, you will get BB plus BC. And then you can see there's a duplication for AB. So AB dot AB, okay, and then another one is AC, BB plus BC. So this is another duplication. So we use the rule for duplication. Here, duplication A dot A is equal to A. So BB here, okay, one of the variables can be cancelled out. So now it's left with B. And then for rule 5, okay, duplication for A plus A can be simplified to A. So AB plus AB. Okay, we can cancel out 1. So you will get AB and then put it down AB plus B plus BC. So then use the rule 10. A plus AB is equal to A. So here we use B plus BC. Okay, when we factorize, okay, B, use the factorize B 1 plus C, which is also is equal to B1. So then you will get B here. Now, AB plus AC plus B. We can use the formula rule 10. AB plus B is equal to B. Okay, remember, AB plus AB is A. Okay, provided that the factor is A there. So now, B plus AB is equal to B. And then plus AC. Okay, so for this example, okay, for the previous example, we have x bar y z bar plus x bar y z plus x y bar z bar plus x y z bar plus x y z. So we use the SOP to apply the simplification using the Boolean rules. So here, okay, we say that, okay, x bar y z bar and then x bar y z. Okay, the first tips is that we find for the 3 input. Let's say we have a 3 input, then we need to find 2 variables. Okay, 2 variables that is similar. So for the first term and the second term, the similar variable is the x bar y and the x bar y here. So pair it together. Okay, so we can pair it together to form the factor. So we write it as x bar y, z bar plus z. Okay, as for x, y bar, z bar. So we can also factor it with the next term, which is x, y, z bar. So the similar term is the x, z bar. So put it plus and then x, z bar. So the difference is only the y bar plus y. Now, what's left is the x, y, z. Okay, so sometimes we can just simplify it with the others, like the other functions that is simplified, or the easiest way is like using the rules a is equal to a plus a. Okay, so a is equal to a plus a means that we borrow or we copy another of the other terms. So let's say here is x, y, z can be simplified together with the x, y, z bar. Okay, so now we use this. Okay, and then pair it together with the term of x, y, z bar. So here the factor is x, y. And then what we get is the z bar plus z. Okay, now since we have z bar plus z, okay, so it's equivalent, okay, to x bar y 1 and then plus x z bar 1 plus x y 1. So if we end it with 1, we will get x bar y plus x z bar plus xy. Okay, so since there is no similar functions, okay, sometimes we can factor it together, such as xy with x bar y. So what we get is that, okay, so y and then x bar plus x plus x z bar. So x bar plus x is equivalent to 1. Okay, the rule is x bar plus x is equal to 1. So what we get is y plus x z bar. So it's a reverse operation. where you can see that, okay, from the Boolean function, you can create the truth table, and then from this truth table, we can try to simplify it and then get the simplified function, okay, as in the picture. Right. So now I will explain about the second method for the simplification of Boolean function. Okay. Now we have a Carnot map, okay, that uses an array of cells to represent the binary values of the input variables. So the number of the cells in the Carnot map is equal to the total number of possible input variable combinations. Okay, so we use the formula 2 power of n to determine the number of cells, where n is the number of input or variables. For example, if z is equal to a dot b, so it's equivalent, okay, so since we have a two input a and b, okay, so two inputs means 2 power of n, which is 2 power of 2, is equal to 4 cells. It's also the same of the number of combination in the truth table. Okay, so we can build up using a map or array of cells. Okay, array of cells like a grid. Okay, and then we separate it. Okay, based on the input variables name. So one is A and B, and then we put a combination of 0 and 1. Okay, so for B we have a 0 and 1, and then for A is 0 and 1. So 1 is a row, A is under the row, and then B is under the column. Okay, so for a function of A dot B, okay, based on the truth table, only combination of 1, 1. Okay, so means that A1 is here, and then column B is 1, then we can put the value 1 on the cell. Whereas the other cell will become a 0 or don't care. Now, how do we simplify it? By using a minimization, resulting in an expression that contains the fewest possible terms with the fewest possible variables. So after mapping the SOP expression into the Carnot map, okay, so the next step is to produce a simplified SOP expression by grouping the ones. Okay, or we can use the output one in the truth table and then export it on the Carnot map. And then we group it. We group the bit one, okay, and build up the minimization or simplified SOP expression from that grouping. So to simplify the Carnot map, we use rules, okay, rules of Carnot map such as a group can contain either 1, 2, 4, 8, or 16 based on the powers of 2. Means that on that group of 1 cannot contain 3, 5, 6, 7, 9, something. So means that it must follow the power of 2. 2 power of 0, 2 power of 1 for 2, 2 power of 2 is 4, 2 power of 3 is 8, and then 2 power of 4 is 16. It must be within this group. So each cell in the group must be adjacent to one or more cell in that same group. So group here means the circle. Okay, the group, we will circle it together. So to circle it together, there must not be any bit 0 in between. Okay, so adjacent means horizontal or vertical. So it must be grouped. Okay, as for the first one, you must group it based on the largest possible number. Okay, so means that you find out if there is a 16-bit one or 8-bit one or 4-bit one, like that. And then lastly, you look okay. At least we must have a group of bit one. But let's say if we don't have any group, then we can group a bit one, okay, separately. So make sure, okay, make sure you group the largest one, and then try to group the smaller one after that. So make sure each one of the map must be included in at least one group. It means for a circle, okay, at least there is one bit that is not belong or grouped together with another circle, okay, so that we can accept that circle, right? So the ones that has already in a group can be included in another group. Okay, you can group it together or circle it together with another group, as long as the circle, that group, okay, include a non-common one, means that one bit there is not included to another group. So so that we can borrow, okay, we can borrow the one bit that is a member of more than one group. Okay, this is an example of AB plus BC plus A prime B prime C prime. Okay, mean A prime and B prime and C prime here. Okay, we group it here. Okay, means AB, A prime, 0, 0, 0. So we put a 1 there. And then AB. So AB means that C can be either 1, 1, 0, 1. So they group it together like this. And then there's a 1 here. Okay, so to simplify it, okay, so this is the simplified version. Okay, in the first place, we look at the truth table and then we put the value of 1, and then the rest, okay, you put a 0. Okay, now to group together, find the adjacent bit. So the adjacent bit is 1, 1 here. So remember, one group can only consist 1, 2, 4. So now we have 3. Okay, 3 cannot be grouped together. So only 2 can be grouped together. So now they group it like this, vertically, horizontally. Now for this group, to simplify it, okay, find the common one, or first look at the row first. Okay, it's on the row 1, 1. Okay, is there any other row on that same circle? No. So we write it AB. 1, 1 here is translate back to the name of the variable. So AB. Okay, A dot B. Next, for the column, okay, so since it's a group, okay, since it's a group of 2 bits, so we look at these 2 bits. So column 0 and column 1. So there's no same pattern here. So 0 going to 1, we can cancel it together. So now it will become AB only. Okay, imagine the combination for this is equivalent to AB C bar plus ABC. So you can group it together, AB, C bar plus C. So which is equivalent to AB1. Okay, then we can cancel that one. So you will get AB, right? So that is for AB. Now next is this group. Okay, the vertical group. Okay, the vertical group here. Okay, so it's on the row 0, 1 and 1, 1. 0, 1 and 1, 1. Look at the same pattern. So this is the first digit is 0, okay, 1, and then the second one, okay, is the first digit is 1, 1. Okay, so the first digit has a change from 0 to 1. So do remember from the previous style that we have C bar plus C. So 0 plus 1 is equal to 1. Okay, now the first digit can be cancelled out. What's left is the B. And then look at the column. It's on the column C. 1 here. Okay, so we can put B dot C for that circle. So now it's simplified as B dot C. Okay, so there's one bit there, okay, that is not grouped together. Okay, it's not grouped together with the others. Okay, so we can just put a one circle for one bit there and then term it based on the value itself, A prime, B prime, C prime. Then we sum it all. So you will get f is equal to ab plus bc plus a prime b prime c prime. Okay, the next one. The next example, as you can see, there's a bit 1, 1, 1, 1, 1, 1, 1 here. So the largest one is this 4-bit. Imagine, okay, how do we want to draw a K-map that is more than 4 combination? Okay, 4 combination. So to draw the 4 combination, AB here, okay, for AB, when we rearrange the cell, it must be in 0, 0, 0, 1, 1, 1, 1, 0. Okay, so why do we arrange it like that? Okay, it's because of we want to cancel out between the adjacent cell. Okay, for example, this one. 0, 0 and 0, 1. The first digit is the same, but the second digit is different. So 0 to 1 can be cancelled out. So it's also the same for the second row and the third row. The first digit here can be cancelled out. Okay, and then between the third row and the fourth row, okay, so the second digit, 1 and 0, can be cancelled out. Okay, and then between the column here, 0, 1, if it's grouped together, it's also can be cancelled. Okay. And then for the second, for the right figure here, as you can see, between the top row and the bottom row, 0, 0, 1, 0, the first digit can be cancelled out. So that's why they have a half circle at the bottom and a half circle at the top, okay, to group together of a 4-bit one. Okay, 4-bit one. So here, as you can see, it's between a row 0, 0 and 1, 0. So what's left is B. B prime, B prime, B bar, and then the column, for the column, okay, since it's a 4-bit, so it includes bit 0 and 1 for the C variable. So we can cancel out the C. So what's left is B prime. Okay, now the rest. Okay, now the rest, we have a bit 1 here, bit 1 here. So we cannot group it diagonally. Okay, diagonally we cannot. Must be horizontal or vertical. So we can borrow. Okay, we can borrow other circles. Okay, other bit circles. Okay, for example, this one. Okay, so we can group it together. So on this circle, we have one bit here that is not belong to other group. So then this circle can be accepted. Okay, now we see that it's under the row 0, 0 and 0, 1. So means that A bar will become the factor. So B will become the cancel. Okay, we can cancel because it's between B bar and B can be simplified into 1. Now, for the column, it's on the column 0. So cannot cancel. So we put it there. We end it A bar dot C bar. Okay. Now for the last circle here, it's on the row AB and AB bar. So the B variable can be cancelled. What's left is A, and then it's on the C column only. So we can just put it down there, AC. Now we sum it all, you will get AC plus B bar plus A bar dot C bar. Okay. Now, for example, the previous example that we have is this one. So we can draw it, okay. The Carnot map can be drawn like this. Okay, previously it's vertical. Now we want to draw a horizontal one. So we want to draw, okay, X, Y, Z. Like that. Okay, so 0, 0, 0, 1, 1, 1. Remember? Okay, the position must be adjacent together. So 0, 1 can be cancelled out with 1, 1. So just remember 0, 1, 3, 2. That's the position. Okay. Now, look at the bit 1. So 0, 1, 0. 0, 1, 0 is 1. And then 0, 1, 1, 0, 1, row 1, put a 1 there. And then 1, 0, 0. So 1, 0, 0, 1. 1, 1, 0. 1, 1, 0 there. And then 1, 1, 1. It's there. Now, okay, so the largest circle that we can have is 4-bit, right? It's very clear there. So 4-bit 0 there. Okay, 4-bit 0. We can simplify it. Okay, first look at the column x bar y and then x y. So here the changes is on the x. So we can take out the x, only leave the y. Okay, we write the y. And then between the z, it's on the row 0 and 1. So 0 plus 1 can be cancelled out. So what's left is y. Okay, the next one is only this bit 1. Okay, so this bit 1, if it's adjacent to another bit here, which we can borrow, so we can draw it. So can the circle can be accepted? Yes, because this one bit is not belong to other group. Okay, so we can accept this. Then we can write it. Okay, this one is x y bar. Okay, x y bar and then x y. So means that y plus y bar can become 1. So we can cancel the y. So what's left is x. And then on the row z, it's on the 2-bit is on the row z bar. So we can just put the z bar. So lastly, we combine it together. So we can get x z bar plus y. Okay, so the Carnot only build up from the truth table or maybe from the SOP. Okay, cannot be done using the POS. Right. Now what's next is that after we derive the expression, we get the truth table. Okay, so in physically it can be built up using a gate. Okay, it can be built up using a gate. So the gate is an electronic device that produces a result based on 2 or more input values. So in reality, gates consist of 1 to 6 transistors, but digital designers think of them as a single unit. Okay, so single unit of integrated circuit. Okay, single unit of gates. So the integrated circuits contain collection of gates suited to a particular purpose. Okay, for example, for the previous example, we have x, z bar plus y. So the purpose is for that function. So when we build up the logic circuit for that, it's specifically to produce that kind of function. Okay, now for the logic circuit, okay, they use the symbol of AND. Okay, the 3 simple gates are AND or AND not, right? So let's say we have a functions, okay, that we have. Now we need to draw it. We can use a simple gate as AND or AND not. So AND symbol is like this, or is like this, okay, and then not is like this. Okay, so this symbol correspond directly to their respective Boolean operation. Okay, as you can see in the Boolean tables. Okay, in the truth table. So let's say we have x z bar plus y. Okay, x z bar plus y. So once we have simplified it, and then we have the function x z bar plus y. So what we need is 3 input, x, and then this is x, this is z. Okay, so since x, z need to be ANDed together, so first is the z bar, and then we draw the AND gate. Now we can write x, z bar there. Now what's next? This one is z bar. Okay, what's next is the y. So OR it. So next you will get f is equal to x z bar plus y. Okay, so that is for drawing the logic gate. Okay, beside the basic gate of AND, OR, or NOT, we have another useful gate which is called exclusive OR gate. Okay, exclusive OR gate, the output of this, or we can call XOR. Okay, the operation is true only when the values of the inputs differ. So refer to the truth table of XOR here. Okay, so the output will become 1 if the input difference have a different value. One is x is 0, y is 1, or x is 1, y is 0. Then the output will become 1. Okay. In terms or in an SOP, x or y, okay, x or gate function, okay, can be represented with x bar y plus x y bar. Okay, so this is one of the useful gate used in the logic circuit. Okay, another logic gates that is very important is none and not. Okay, they are what we call as universal gates. Okay, the symbol and truth table are shown at the right side. Okay, how they build up the NAND gate comes from the basic AND, and they knot it together. Okay, so this is the original one. So they AND it and then put a knot there. Okay, put a knot. So what we get is x, y bar. So the result or the output will become, if it's not 1 and 1, so the result will be 1. Okay, and then the complement or the its equivalent, okay, logic design for the NAND gate, okay, can be represented using an OR gate that previously is not on the input. So x bar and then y bar, and then we OR it together. So how do we derive this? Since x, y full bar can be converted using a De Morgan theorem, so we break the full bar here to become x bar or y bar. So you can get the same truth table actually. Whereas for the NOR gate, okay, the NOR gate is the complement of the OR gate. Okay, so they OR it and I put a knot there. So what happened is that only bit 0, all input 0 will produce output 1. Then that is the NOR gate. So it will produce the function x plus y full bar. And then it can also be represented using the De Morgan's theorem, whereby we NOT it, okay, we NOT it, the input of x and y. So x is not, then y is not, and then AND it together. Okay, so what is none and no? Okay, they call it as a universal gate because they are inexpensive to manufacture, and any Boolean function can be constructed using only none or only no gate. Okay, this none and no gate can represent the not function, the AND function, and the OR function. Okay, so that's why we call it as universal gate. Right. So gates can have multiple input. Okay, and in the first place, when you see and or have two inputs, right, and then not have one input. So sometimes, okay, sometimes gates can have a multiple input and more than one output. Okay, so as you can see here, for x plus y plus z, okay, so have one output, and then x, y bar z has one output. But there's sometimes have second output here, Q and Q bar. So note that the second output can be provided for the complement of the operation. So we will see more of this later. Okay. So the main thing to remember is that combinations of gates implement Boolean functions. Okay, so the circuit below implements the Boolean function x plus y bar z. So based on this function, we derive the truth table first, and then we simplify it. Okay, we simplify it. Okay, to get the simpler circuit. To get a simpler circuit. So here we can say, we can look that, okay, y is not together, we not it, okay, and then we end it together, so you get y bar z, and then OR it with the x, so you will get x plus y bar z for your circuit. Okay, so that is for logic circuit.